I'm Peter Taborek, and I'm the PI of the Learning Labs project implementing and testing adaptive learning software for introductory physics, chemistry, and engineering classes. This is a collaboration between the physics and mechanical and aerospace engineering departments at UC Irvine, the physics department at Orange Coast College, and the chemistry department at Golden West College. And the whole team is really excited about working on this project, and we're very appreciative of the funding from the governor's office to pursue it. Deliverable for this project are going to be 5 quarter courses, a 3-quarter sequence of introductory physics for scientists and engineers, a 1-quarter course on preparation for general chemistry, and a 1-quarter engineering dynamics class, which overlaps strongly with the introductory physics class. These are introductory STEM classes that are taken by tens of thousands of people throughout California every year. Our goal is to build an online course system that is interactive. By interactive, I mean not simply static PDFs or even videos, but something that requires for the learner to actually interact with the software. An automatic grading system, both for prompt feedback to the student, but also a scalable solution to run large classes. We'd like to make it adaptive, and I'll explain that further in a moment. We have built them all based on open source texts, and that allows us to make the whole learning platform at a very low cost. I want to contrast that with the status quo, which is our students currently are required to buy proprietary textbook and grading systems. And for a sequence like the ones I just described, will cost the students over $400. And they are, of course, traditional static textbooks, and they are non-adaptive. In other words, all the students get the same content and the same problem sets. And anyone who has taught introductory STEM classes knows that there is typically a very wide range in the initial preparation of the students that come into these classes. And in fact, that wide preparation and the difficulty accommodating it is both what makes teaching it hard and also leads to student frustration and failure. Our goal is to build a system that programmatically delivers content and problems which are individually tailored to a learner. And the idea is to guide that learner to mastery. In the traditional model, all learners are treated the same. There's a group of assignments. They all do the same assignments. They all get the same quizzes, and they all do it at the same pace. And how they perform on these individual assignments has nothing to do with the sequence of learning. Adaptive learning, on the other hand, is quite different. The same topics get covered, but the assignments and the progression through the subject matter are tailored to the individual student, and it is directed, and it depends on how the student responds to certain problems that they have to solve. And if a misunderstanding is discovered, then the system will attempt to address it by providing additional content that will reinforce that content and then allow the learner to go back and accomplish mastery. In order to implement a plan like that, there are 3 main things that 3 components that we need to build. First one is a software system that contains the content, the problems for assessment, and the records of the student, all the student responses for all the problems in one coherent database. And that's currently not the case, and is required to make truly adaptive learning, because we need to know both about the student and about the content and all possible content. So we need to have it all in one database. The questions and problem sets that we give the students also have to have tags, which will give information about their difficulty and what prerequisite skills are required to do them, and so on. Because again, the adaptive algorithm needs to understand what kind of problem we want to deliver next based on the students' responses. So we need to have information about the questions. And then the final thing that puts it all together is an adaptive algorithm, which delivers content, assesses the student, and then delivers new content based on what they did. And that's illustrated in this diagram. There's an adaptive engine, and the basic idea would be that students are given first simple problems. Depending on their response, the difficulty will be ramped up, and again, with the idea of achieving mastery. And until mastery is obtained, they cannot move on to the next subject. So we can reinforce mastery by delivering additional content, additional hints, and additional work. And then if a gap in the student's understanding is discovered, then the software would direct the student to appropriate mediation. Now, of those three important things that are required to do this, the adaptive learning algorithm is the most complicated and sophisticated and difficult. And we are working on it, but we really we will not have a functioning version of this until probably summer of 2021. But the other two pieces, in other words, the software that delivers it and the question banks for that software, we've actually made quite a bit of progress on already. This is our preparation for general chemistry class, which one of our team members, Stanley Hugh, has been working on. And this is the platform that we use to deliver it, the software. We've paid quite a bit of attention to making software that's simple to use and aesthetically appealing, and we've broken it up into pictorial modules like this that illustrate, that give the frame the subject matter for the student. As I mentioned, we use a open source textbook, so there's a high quality textbook that explains some of the material. We can put reference material that's available to the student at all times, and we have interactive components that shows, for instance, molecular structure and lets the student interact with the content. We also have a introductory physics mechanics theme, which is laid out roughly the same way. We often put explicit learning goals to direct the student's attention. There's again a textbook that explains some of the material. And then we have interactive treatments of the fundamental problems of that subject. So this is work, and so we're going to talk about work of a mass sliding down an inclined plane, one of the prototypical problems of this field. And this kind of software allows the student to study the subject and to go through the derivations one step at a time and be very explicit. We found this is much more effective than video because it goes too fast otherwise. And this just shows exactly every step of the problem. Once the student has actually worked on these problems, the quizzes sort of look like this, and we can build nicely formatted multi-part quizzes. And once the student is done with it and it's been graded, then there's a solution will pop up, and again, it's very detailed. It explains exactly how to do the problem in detail. The way these problems are generated is with something we call the quiz engine, which is a piece of software that lets you compose these kind of problems, and it lets you, and we're starting to build the tags, so we can build tags that identify the various characteristics of the problem, and then in the end there is code that can be done in either JavaScript or Mathematica that interprets the answer and basically does the grading.